Welcome to this explainer. Today, I'm taking you on a direct walkthrough of my newly rebuilt local AI architecture. We're going to pop the hood and see exactly how I moved from a neatly packaged development environment to a fully modular open source stack. It's a fun one, so let's dive right into how it was all built, tested, and benchmarked.
Right off the bat, let's be totally clear about what we're looking at here. This isn't some massive production enterprise server sitting in a climate-controlled data center somewhere. Actually, it's just a repurposed workstation, but I've intentionally rebuilt it as a highly controlled local AI test lab. It's designed specifically to model the exact enterprise-grade layers that your infrastructure teams deal with literally every single day. Section 1. Why rebuild Belag? So previously, I was using the NVIDIA AI Workbench, and don't get me wrong, that platform is absolutely fantastic for validating GPU acceleration quickly, mostly because it abstracts all the heavy lifting. But you know what? That abstraction was exactly why I needed a change. Building this custom open source stack forces you to really expose and manage the underlying operational layers. By taking this modular route, you're forced to learn about host stability, GPU driver management, container runtime configurations, and persistent storage. It's the exact same design, security, and scaling layers you'd find in a real enterprise environment.
Section 2. Hardware and open source stack.
Let's talk metal. Our host hardware features an Intel Core i7-7800X processor that gives us 6 physical cores alongside a really solid 128 gigs of RAM and a fast 2TB NVMe SSD. But the real star of the show? That's the NVIDIA RTX 360 with 12 gigabytes of VRAM. Now, in the enterprise AI world, 12 gigs of VRAM is, well, practically a rounding error. But that's exactly what makes it the perfect constraint for our capacity testing. We want to see exactly how hard we can push this specific footprint.
To run on that hardware, we deployed a super lean open source software stack. We're running a Windows 11 host with an Ubuntu Linux environment living right in WSL2. From there, we use Docker Desktop as our container platform, Ollama as the local model runtime, and Open WebUI to tie it all together. The absolutely crucial point here is isolation. By keeping all the AI tools locked neatly inside containers, the Windows host remains perfectly clean and stable. No dependency conflicts, no messy registry entries, just clean, modular architecture.
Section 3. Validating each architecture layer. This brings us to a highly disciplined principle of stacking. You can't just jump straight to downloading massive AI models. You have to validate every single layer, from the operating system all the way up. Step 1, make sure Windows is stable. Step 2, cleanly install WSL2. Step 3, get Docker Desktop running. Step 4, and this is the absolute critical go or no-go test. You gotta validate that your container actually has access to the GPU. Only after that path is totally proven do we deploy Ollama in Step 5 and our UI in Step 6. Measure and validate first, then expand. Section 4, model testing and benchmarks. So this poses the exact operational question that infrastructure architects always need answered. How far can a 12GB RTX 3060 realistically go with modern local models? Before deploying to production, we really need to understand the VRAM limits, the power draw boundaries, and the true capability limits of our hardware. Let's see what happens. I tested 4 distinct local models to find our interactive workflow limits. First up, Qwen 3.4b for fast general reasoning. Next, Gemma 3.4b, which is absolutely fantastic for multimodal vision tasks, like, say, reviewing screenshots of server racks. Then we stepped up to Qwen 3.8b, which is designed for your daily infrastructure reasoning. Finally, we deployed Qwen 3.14b to serve as our heavy-duty, practical upper bound test on this 12GB card. Let's look at the hard benchmark data between our 2 largest models. I ran the exact same infrastructure architecture prompt through both. The Qwen 3.8b completed the end-to-end task in 59.34 seconds. The much larger 14b model? That took 93.80 seconds. So while the 14b model is roughly 58% slower and pushes the power draw right up to the card's 170-watt limit, it surprisingly completed the run completely successfully without crashing. No way, right? But here is the most crucial telemetry metric of this entire explainer: 100%. Both the 8 billion and the 14 billion parameter models achieved 100% GPU residency at a 4096 token context window. That means they fit entirely inside the VRAM without spilling over into CPU offload or system memory. If they had spilled over, it would have absolutely tanked the latency.
Section 5. The practical strategy forward. Based directly on the data, here's the practical conclusion. Qwen 3.8b provides the absolute best capability to responsiveness balance for this specific 12GB hardware footprint. It leaves enough VRAM headroom, it runs cooler, and it's highly responsive. For sure, that makes it the default daily model. The 14B model is still incredibly useful, but actually it should be reserved strictly for deeper, selective analysis where you are perfectly fine accepting the added latency and maxed out power draw.
So what's next? Now that the foundational model layer is proven, the next phase of the lab is introducing our first real enterprise workload. We're going to build an AI infrastructure co-pilot. This means deploying vector databases and retrieval workflows, RAG, to ingest sanitized bills of materials, statements of work, rack layouts, and vendor documentation. We are taking this from a simple chat interface to a grounded, deeply integrated infrastructure design assistant. It's going to be a real game changer. As we wrap up, I want to leave you with this final, powerful thought from the project. The hardware changes at enterprise scale. The architecture thinking does not. Whether you're building on a single RTX 3060 workstation in your home lab or a massive cluster of high-end GPUs in a secure data center, the operational questions of VRAM boundaries, container isolation, and model size trade-offs remain exactly the same. Master the architecture here, and you're ready for the enterprise scale. So what infrastructure challenge are you going to build for first?